And we are live. Okay, so as predicted last week, little Miss So-and-so has been to the hairdresser and we can see her eyes temporarily. So in a few days I won't be able to see them anymore. You can see this fur above the eyes is already starting to grow out to try to hide them. But she's very sleek right now and I appreciate it. Okay, so now she still smells good too from the doggy shampoo. Okay, putting you down. Lie down. Go sleep. After the lesson, it will be supper time, but not yet. Okay, and this is the West Bromwich Albion shirt. Pretty little shirt. And let's get into the math. We are doing geometry. We are still doing geometry. We are doing surface area this week. Now, I already have a drawing, a net drawing, also known as a net, on my chalkboard wall, which I made out of this. Now, as you can see, this little box, which is full of staples, is a lot smaller. So this drawing is a scale drawing where the drawing is larger than the object. And how did I do that? Well, you can see a bit of evidence right here as to what I did. What I did was I measured, and I used inches for this, I measured the length, width, and height of this little box, and I wrote the values there. And when I did this net, I multiplied each of those by 3. So I ended up doing a larger drawing, which is useful, of course, because it's on a chalkboard wall, and little tiny drawings would be hard to see. So there was a reason to do that. And of course, I can find things like the surface area. Yeah, that's what this lesson is about. The total area of all 6 of these rectangles on this little box. I can find the surface area of this using formulas, but I can also find the surface area of this expanded version of the same thing. But when I decided to start recording this particular lesson, I decided that I didn't want to multiply all of the side lengths of these rectangles by 3. I want to do a brand new net, and I'm going to do it right here beside the original one, and I'm going to multiply all of the dimensions by 4 instead of 3. So what is the result of that going to be? It's going to be a net that looks very similar to this one, but it's going to be bigger. And you can sort of get an idea of how much bigger. So everything was multiplied by 3 in order to get this drawing. Now I'm going to multiply all of those dimensions by 4, and we'll see what the drawing looks like, and we'll compare them. That's the way I wanted to begin this lesson. But before I start drawing, I'm going to talk a little bit more about nets and what we can do with them. I highly recommend that students who are starting to study this sort of geometry, the 3-dimensional geometry, these solid shapes, that students experiment with nets. Nets are fun to draw. They're not very difficult to draw. But you have to take your time. There can be little moments where it becomes challenging, but those moments are happening because the student is learning something. And even though I'm supposed to have already learned all of this stuff before, when I draw something like this, I feel like I'm learning something. I feel like I'm in the lab. It's not just theory anymore. I'm doing something that's sort of practical and hands-on, and it makes me feel like I'm learning better. This geometry that I already knew. Okay, so what is this? This is a net drawing of a cube. How do I know it would become a cube? Well, we can see that it has 6 faces, which are all squares. And if we were to cut this out and fold together along the lines, we would be able to make it form a cube. Well, I guess I could reveal what that would look like by holding up this thing, because I made a copy of this. When I made it, I made a copy, and then I took one of the 2 copies and I did cut it out. Now, of course, you see that there are these extra little trapezoidal shaped things here. Here I put 3 of them in strategic places because I knew, sure, I can fold along these lines and it will fold together to form a cube, but how am I going to get the cube to stay together? That's a little tricky. So you can see on this face where all 3 of my tabs ended up, and I put a bit of glue, and that allowed me to make this thing hold together. So it becomes kind of fun to do. This is not a strong object. I do not want to accidentally sit on this. It won't last long if something like that happens. So I recommend that students do net drawings, and it's always a good idea to start with some of the simpler shapes. The cube is one of the simpler shapes. There are going to be less surprises in store for you as you make that net and have it work. Because when you cut it out with scissors and fold it together, that's when you find out if you actually did it properly. How long is the side length of these squares? Now, this is a normal 8.5 inch by 11 inch sheet of paper, so that could give us a bit of an indication. I managed to make this net drawing just about as big as I could make it and have it still fit on this page, and I did that with a strategy. The side length of these squares is 2.5 inches. So their strategy comes right into this, right from the beginning, because you can draw a beautiful net that goes off the page and then it will be incomplete. So making it fit on the page has its own challenges. And like I say, while that's happening, you're learning. Okay, it's not the only one I did though. I also did this one, which is again one of the simpler ones. It is a triangle pyramid, which has an equilateral triangle as the base, and in fact all four of the faces of this thing are going to be equilateral triangles that are the same size. And I think I used 3 inches for the side length. I have it written down over there because I'd like to find the surface area of this thing as well. And I will do that. Okay. But I also made a copy of that one and glued that one together, and you can see some tabs there. Is there another tab? Yes, there's another tab here. So I made tabs so that I'd be able to make this happen at the end, and it was kind of a strangely satisfying exercise. Okay, now let's get back into this one. Now remember, this is a net drawing of this box of staples, but I changed it so that it would end up bigger because I wanted to do it on my chalkboard wall. So I'm going to do another one, and instead of multiplying all the dimensions by 3, I'm multiplying by 4. So I think I should get busy doing that now. 4.5 times 4 is going to be 18 inches. 1.75 times 4 is going to be 7 inches. I better double check all of these. I've learned my lesson. 1.4 times 4 is 5.6 inches. So I know the side lengths of the various rectangles that I'm going to have to draw, which I will draw over here, and they will be a little bigger. Because this line here is not 18 inches. It was 3 times 4.5, so it was 13.5 inches. Now I'm doing 18 inches. I hope it's going to fit. Let's find out. So I'm going to start, and again, strategy comes into play. I want to make sure the drawing fits. I'm hoping that I can put it right here and have it fit in the camera angle, and I don't really want it to go up and overlap with this title, which I decided I wanted to leave here for the whole lesson. I don't want it to go too low and go right off of the camera angle. Well, I guess we'll see if that's going to work. I'm going to start by drawing an 18-inch line, and I'm going to make that line horizontal. I think that will help me to make this fit. So 18 inches, let's see. I'm able to go right over to here, so I want to make sure I have enough room. I have to have enough room for these two little side rectangles that I'll eventually draw. I'll draw those last. So I'm going to start with the top rectangle and then continue downwards to make sure that these will fit. Whew, it might be a little tricky. I'm going to start right up close to this title to give myself the best chance of making it fit. Now 18 inches, that's here. That gives me a little bit of extra room, a little bit of extra wiggle room. Okay, I'm starting by drawing an 18-inch line. It would help if I could draw the line straight. And there it is, there's 18 inches. Then, the biggest rectangle will be 18 inch by 7. So the next thing I'm going to do is draw a perpendicular line that's 7 inches in length. And I am judging my 90-degree angles by eye, I admit it, because I don't have time to get out the protractor and be too picky. So if these two endpoints, and I connect them, are 18 inches apart, it means I did a pretty good job of that, and I'm happy to say that looks like I did. Okay, I have drawn a rectangle which is 18 inch by 7 inch. What do I have to do next? Remember, we want the net to be able to fold together. So what I drew was the biggest rectangle, so on this actual staple box, I drew what was either the bottom or the top. That's the biggest rectangle. This one on the side is not quite as big. Still the same length, but not as wide. So the next thing I have to do is draw another one right here, which is going to be 18 inches. So I'll reuse this side, but by 5.6 inches instead. Let me get my calculator. I forgot to double check my calculations. Yes, that's fine. Yes. I've learned my lesson, but I'm still happy when I do calculations in my head and they are correct. Okay, so now I want to draw a rectangle that connects to this one, which is 18 inches by 5.6. So that means I'm just making this line longer by 5.6 inches. There. And this one, same thing, 5.6 inches. And now I connect these together with another 18-inch line, which is working out fine. And I hope we can see by eye that this new rectangle is not as wide as this first one. I think we can see that. And we can see the same thing here. The shaded ones are the biggest rectangles in this drawing. Okay, so now what I need next, it is actually kind of becomes easy, and some of the steps of it are easy. I need another 18-inch by 7-inch. So I'm just going to keep on drawing it, and then I'm folding downwards here. 7 inches. 7 inches. Connect these together with another 18-inch line. The lower I get on the chalkboard wall, the more awkward this gets. But I did it. Okay, and now I need a fourth rectangle, which is also going to be 18 inches by 5.6 inches. So let's do that. Good. Pretty good. And connect these two together. 18-inch line. Is it 18 inches apart? It sure is. I'm happy with this. Okay. We've got a lot. We've got a lot in this drawing. What I have to do now are the two little rectangles. And you might notice in this one that I did something creative. I tried to make it extra challenging for myself, and I'm going to try to do the same thing again here with this bigger drawing. Because I could just put the two end rectangles, that's these two smallest rectangles you see here and opposite face, I could put them both at the same height and then they would both be oriented the same way, but instead I put one of them along this bigger rectangle and the other one along the skinnier rectangle, so I had to orient the two rectangles that I drew, which are the same size, but I had to orient them differently. One of them is a 90-degree rotation. Interesting. So what I need now to do that is I'm going to do, this is already 5.6 inches, so I have to draw out by 7 inches, and that will fit. Now I can see that my strategy is working, it's going to fit. So there's a 7-inch side, need another one here. And then this is going to be 5.6 inches. I have that little side flap. There's only one missing. I'm going to put it here. But this is the 7-inch side over here. So if I'm drawing out from it, I have to draw out by 5.6. And that will just barely fit in my little space I've given myself. 5.6. 5.6, and connect these last two vertices and I am finished. Not bad. So I have drawn another net of the staple box, but it's bigger. And so it is a scale diagram net of that staple box. And finally that means I guess I can erase this one. So we can compare them. You can see really it is the same drawing, except slightly different strategy. Here we put one of the skinnier rectangles on the top. So it's skinnier, wider, skinnier, wider. This one we started with one of the wider, skinnier, wider, skinnier. Otherwise the strategy is really similar and you can see that it works. So the net drawing works, and the net drawing is so useful because we can use it to calculate the surface area, which can be a little awkward to do sometimes with an actual 3D object because you can't even look at all of the faces at once. So I can see one of them very well, and you can see the opposite face very well, but I have to sort of swirl this around to work with it, whereas with the net, I can see everything. So let's calculate. I'm going to erase the old net drawing, and I'm going to calculate both the total surface area of this new drawing and the total surface area of the little plastic box. And we will take a look at those. Okay, so we have two rectangles which were both 18 inch by 7. The area of a rectangle, of course, is base times height, which is going to be 18 times 7, which is how many? 56, 126 square inches. But then there are two of those, so that the two I'm talking about right now are the two that I am shading. So I want to say times 2 equals 252 square inches, but we are not finished. We have found the area of 2 of the 6 faces of our rectangular prism. So now we are going to do the same thing. The area, it's all rectangles, so I'm just always going to use area equals base times height. So filling in the formula, for this slightly smaller rectangle, it's going to be 18 times 5.6. Which, yes, I'll get my calculator to do that. 18 times 5.6 equals 100.8 square inches. But again, I have to multiply by 2 because there are two faces that size, equals 201.6 square inches. And of course, we're not surprised to see that the total area of those two biggest faces is a bit bigger than the total area of those two medium-sized faces. We still have to do these small faces. And they are the same even though I oriented them differently. The area is base times height, and it's going to be 7 times 5.6. Yes, 7 times 5.6, which is 7 times 5.6, 39.2. Times 2, because there are two of them, equals 78.4 square inches. We're still not finished. I have to add all this together. So I will do that here. 252 plus 201.6 plus 78.4. I think one of the biggest challenges of doing this is having so many calculations and so many numbers and making sure not to miss something or to use the wrong number. But I think I'm being pretty careful. So 252 plus 201.6 plus 78.4 equals 532, a nice clean 532 square inches. Now I want to find the total surface area of the little box, for which I am going to use these original dimensions, the 4.5 inches, 1.75 inches, and 1.4 inches, but otherwise the calculations are going to look very much the same. So I'll move this dangling yardstick out of the way to make a bit of room. We have 4.5 times 1.75 equals 7.875, but that also I have to multiply by 2 times 2 equals 15.75 square inches. Is this fitting into my video rectangle? Yes, it is. And then we have 4.5 times 1.4. 4.5 times 1.4. 6.3 times 2 equals 12.6. And then we have the 1.75 times 1.4. 2.45 times 2 equals 4.9 square inches. I am really running out of room on this chalkboard wall. I may have to do a calculation in the middle of my drawing at the end, but I am going to be able to add these together. More chalk, please. And that will be 15.75 plus 12.6 plus 4.9. And again, I'm being careful to make sure I use the correct values. 15.75 plus 12.6 plus 4.9. 33.25. It's just going to fit. I think maybe my unit might not fit. I'll put it here. 33.25 square inches. Okay, so one last question that I want to ask before I erase all of this and do some other shapes. But this was fun. It was a fun little experiment to do this thing. We have the total surface area, 33.25 square inches of this thing. Total surface area of this thing is 532. We did everything between the two, the plastic box and the big net drawing, by multiplying by 4. Is the area going to be 4 times as big? What will happen if I take 33.25, which is the area of the little box, and multiply it by 4? Am I going to get 532? No, I got 133. Interesting. Interesting. That is something that is worth thinking about. But what if I take that 33.25 and I multiply it, instead of by 4, I multiply it by 16. Ooh, where can I write this? 33.25 times 16 equals exactly 532. I just won't write the units. Why would it be 16 instead of 4? That is something that is worth thinking about. But I'll leave that as part of the math lab exploration for a student to try and come up with an answer to that question, because it goes beyond the scope of the lesson plan I have planned for today. What I want to do now, okay, I did my net drawings, I showed my actual cutout net drawings, I did this thing, that was really fun. It's too bad I have to erase it now. What do I have left to do, and how much time do I have left to do it? I've already used more than 20 minutes of the planned hour, but I can at least do a lot of erasing and make room to do some other stuff. So I'm going to do that. I'm going to leave this label surface area up on the wall, because the whole lesson is going to be about surface area. Erase all these calculations in that wonderful drawing. And look at my notes and decide what else it is that I want to cover. Now, the last time I did this, I found the surface area of some spheres, and this is one of them. It's a lawn bowling ball. It's very dirty. But I decided I don't want to reuse that. I want to find the surface area of some other spheres. So I was thinking, what other spheres are there that are interesting that I guess students won't encounter as much? And I came up with some interesting ideas. So I'm going to find the surface area of some spheres. And since I'm talking about the sphere, I'm going to rate the word sphere. Of course, we're surrounded by spheres all of the time. It's just that we usually call them balls. But balls are spheres. And the sphere is interesting. Why is the sphere interesting? Because it is a three-dimensional object. It is a solid object. It has volume, although we're not covering volume yet. It has surface area. But it doesn't have faces, the way the staple box has these faces. So those familiar area formulas that we use, like we use so many rectangles for this, don't come in very handy with the sphere. So that's one of the things that makes the sphere a different type of three-dimensional object. And of course, these triangles, I can find the area of the surface area of this triangle pyramid by using the triangle area formula. Again, we have formulas that we can use. But with the sphere, we're not going to use the circle area formula for the sphere. We have a formula for the sphere, which is this. The area is equal to 4 pi r squared. And you see some familiar stuff. There's pi. Okay, so something's about a sphere is circular, and then when you get into circles, pi is involved in your formulas. There's pi. Pi r squared, we can take away the 4 and we say, oh, pi r squared, that is the area of a circle. Why would the area of a sphere be exactly 4 times as big as the area of a circle? Well, that's an interesting question in itself. All sorts of interesting stuff happens with the sphere. But one thing that's cool about the sphere also is that spheres are kind of easy to deal with, because the only thing you have to know in order to be able to find out anything you need to about a sphere is the radius. And that means that's kind of like the circle in that sense. The radius or the diameter, but of course if we know the diameter we can figure out the radius very quickly, and we're not putting diameter into this formula, it's radius that we need. So with a sphere, as soon as you know a diameter or a radius, you can get busy and you can find out all sorts of things, including the surface area, which we are going to find out. We can also find out the circumference. A sphere still has a circumference, even if it is a three-dimensional object. Interesting stuff, the sphere. What other shapes are there? I'm going to make a little list of the ones that I've covered so far. We have seen a little bit of the triangle pyramid. But you can also have a pyramid that has a square as a base. So I'll mention the square-based pyramid. And actually, after you go triangle, then you go square, then you go pentagon. You can have a pentagonal-based pyramid. You can have a whole lot of pyramids with different shapes as the base. That's kind of interesting, but I'm just going to mention the triangle pyramid and the square-based pyramid. And then there are the prisms. Prisms, now, we did already deal with the rectangular prism, so I guess I should list it. Rectangular prism. So what's the difference between a rectangular prism and, say, a rectangular pyramid? The difference is that the pyramid comes up to a point, and the prism, the shape on the bottom, stays intact all the way to the top. So that's the way I like to remember what a prism is. A prism, there are all sorts of shapes that are prisms. A cube is a prism, because a cube is following that rule. The shape on the bottom is a square. This square is 2.5 inches by 2.5 inches. And the shape on the top, the face on the top, is also a square with 2.5 inches by 2.5 inches. So that makes a cube a prism. But we don't usually refer to a cube as a prism. We usually refer to it as a cube. And that's convenient. Cubes are so useful in our all sorts of applications. Like, what is it? What can I think of that? Oh, there you go. So there's something. We have this dice, which is a cube. We have sugar cubes, which are cubes. Cubes are useful. So it's useful that they have their own name. But a cube is also a type of prism because it follows the definition of a prism. And then the triangle prism. Some of these things are not so easy for me to draw. But here's I'm trying to draw a triangle prism, and I'm starting with an equilateral triangle. And I'm just going to draw another one the same size. And then I'm going to connect, let's see, I'll connect like that. And then this edge would be in the back where I wouldn't really be able to see it if I had the actual 3D object. So therefore I use a dotted line to show that I can still see it. It helps me see the shape. And it helps me decide, okay, which of those 3 long edges of the triangle prism is in the back, while the dotted line one is in the back. So there you go. So we have rectangular prism, we have the cube, which is a prism, and I'll mention a triangle prism. I guess I should say triangular prism. And again, much like with the pyramids, there can be other shapes as well. You can have a pentagonal prism, etc. Interesting. Lots of interesting stuff happens there. How would we find the area of this? The area would be the total of the area of these 2 triangles, which would be equal to each other, and the area of these 3 rectangles. Interesting. When you get into the 3-dimensional geometry, so many things can happen. You think you have one simple little shape, and it turns out it's a whole lot of possible shapes. I think my favorite is the rectangular prism. because simply by making any of these lengths, well, I don't have the lengths anymore, this longest length, this medium length, that shortest length, changing any of them gives me a new rectangular prism. If I want to come up with a lot of examples and have students find surface area of a whole lot of rectangular prisms, all I have to do is change one of the dimensions, and I've created a new question for the student to practice with. That's good. I'm going to take a little break to take a sip of my fizzy water. And stretch my shoulders. And look at the time again. Okay, now we're at the halfway point of my lesson. There is so much, just in all these shapes that I've mentioned so far, there is so much that it's just far too easy to fill an hour with interesting examples. There's no way we could cover all of the interesting examples, so we sort of have to pick and choose and do a few highlights. I think we could have a whole year of lessons about three-dimensional geometry, and we would never run out of different examples, because that third dimension adds more than one extra example. It adds so many different things that can happen. Okay, so what am I going to do next? What I'm going to do is I'm going to do some spheres. I want to make sure to fit the spheres into the lesson. There's my surface area. That's really what I'm focused on. But of course, once I know the radius of a sphere, I can calculate other things besides the surface area. I could calculate the volume, but I won't. I can calculate the circumference. Now imagine a ball, and you dip it in paint, and then you just start rolling it down a slanted driveway or something like that. If you put just one blob of paint on one side and you roll it, you could see spots of paint appearing and how far apart would the two spots of paint be? That would be the circumference of the circle. It would be the circumference of the sphere. So there is a circle there. And when you think about the circumference, you're visualizing the circle that this sphere looks like if we couldn't see in three dimensions, if we couldn't see the depth, you'd think I was just holding up a circle. So we could find the circumference of that circle because all we need is the radius. It's the same radius we need for the surface area. We can find the diameter, of course. So let's do a couple of examples until I think I've used enough time. So what examples did I come up with? Coming up with different things besides the balls that I have in my backyard. I have a basketball, a soccer ball, I have a lawn bowling ball that you've seen, a ball for playing ball hockey, and then there's some other, but I was thinking, what about some bigger ones? So I was trying to think, what bigger balls are there? So the biggest ball I could think of is an earth ball. I have met students who've never heard of an earth ball, but I have played with an earth ball. It's actually a really fun thing to play with. And I'm sure they come in different sizes, but when I started doing research about what a standard size might be for an earth ball, I saw one where the radius is 5 feet. So I want to find the surface area of that earth ball. Imagine a radius of 5 feet. I'm 6 feet tall. So radius, that's just the radius. That means that the diameter, well, if the radius equals 5 feet, the diameter, that's a really messy V. The diameter is equal to 2 times the radius, which is 2 times 5, which is 10 feet. That is a big ball. And that's fun to play with. It's hard for even one person to even move one, which is kind of the whole point. It encourages teamwork. Cool ball. All right, so we found out already for our earth ball, I'm going to write the word earth ball. We've already found out one thing. Given the radius, we know the diameter. Let's find the surface area. The area is going to be 4 times pi times 10, no, radius is 5, times 5 feet squared. Following the order of operations, I want to square the 5 first before I do my multiplying. 4 times 3.14 times 25. Oh, this turns out to be an easy one to do because 4 times 25 is 100, and 100 times 3.14 is going to be 314 square feet. That's a lot of area. That's a big ball. The earth ball is big. And of course, we can find the circumference. We can find the volume, which I'm not going to do. I guess I'll just do the circumference and then I'll stop. Circumference is equal to 2 pi r. I'm choosing to use this version of the formula, which is 2 times 3.14 times the radius is 5. Oh, this is an easy one to do as well. 2 times 5 is 10, times 3.14 is 31.4 feet. 31.4 feet all the way around the ball. That's big. So that's cool. What other big ones did I find? That was the biggest one. Of course, you can do things like the moon and planet Earth, etc. But I didn't want to go that big. I wanted to go big, but still be a ball. A ball that people actually would use the way we use balls. Like the medicine ball. There's a pretty big one. Bigger than a basketball. Okay, so let's do the same thing with the medicine ball. So we can practice using this formula. I'm not going to do the circumference or even the diameter with the medicine ball. I'm just going to give the radius and then find the surface area. The medicine ball, and again, medicine balls can probably be different sizes, but the one I found had a 7-inch radius. Therefore, the surface area is 4 times pi times 7 squared. 7 squared is 49. 4 times pi times 49 is going to give us 4 times 3.14. Yes, I'm using 3.14 for pi through the whole lesson times 49. 615.44 square inches. We did it. Okay, so it's kind of an interesting lesson about the sphere. That it's cool, it's different, it's interesting. It doesn't work the same way as all these other three-dimensional shapes, but it's still a three-dimensional shape. And it still has surface area, but it feels too easy. Because really, the only variety we get is, well, how long is the radius this time? That's really the only thing that changes with the sphere. How big is the radius? So you change the radius and you do the formula over again. And there's only so much you can do with that. Besides all these other formulas that we're not going into in today's lesson. What other types of ball are smaller than an earth ball, but bigger than a medicine ball? I forgot to write the word medicine ball, but I won't bother. What other types of ball are there in between? Okay, so again, we're talking about some rather large ball, and the one that popped into my head is the exercise ball. Don't really play with it in the exact same way that you play with a lot of these other sports balls. But the exercise ball is useful. It's great for doing your crunches while lying on top of, although that takes a bit of getting used to. And it's a good way to look, to make people laugh when you're in the gym if you don't know how to do it well. But I found exercise balls, and they come in different sizes because they're designed to be the right size for different sized people. So I found 5 standard sizes. And I may as well get into some metric system, because why not? Because we have to be able to deal with standard measurements and metric measurements. So I found 45 centimeter, 55 centimeter, 65 centimeter, 75 centimeter, and 85 centimeter. That sounds logical. Someone decided that they liked for these, and these are diameters. Someone decided they liked these diameters to keep on ending in 5 and just add 10 centimeters each time you increase the size. So I will just pick one of those. So the exercise ball how about I choose the medium one? The medium one is 65 centimeters. 65 centimeters. Okay, the fact that we are doing metric doesn't change anything except our unit. So we'll tag the correct unit on at the end. The area is going to be 4 times pi times 65 squared. And of course, everyone knows 65 squared is 4,225. So 4 times 3.14 times 4,225. But I will get my calculator to finish this. 65 times 65. Yeah, 4,225 times 4 times pi, which means times 3.14. 53066. 53066. This is centimeters squared. And of course, if we find that measure in inches, it's going to be about 26 inches, but that's not a perfect conversion. But if we were to have the radius, oh, I made a mistake. I gave the diameter, but I used it as if it was the radius. I have to do this over again. I'm going to do it over again. So it's not 65 centimeters. Now I'm embarrassed. Half of 65 is 32.5, right? 64, yes. So the radius is 32.5 centimeters. It is time for me to correct my mistake. Let's erase. And we are doing 32.5 squared, and no, I'm not going to do that one in my head. 32.5 squared. $1,056.25 times 4 times pi, 13,266.5 centimeters squared. Okay, and this is a really easy mistake to make. I can almost say I'm glad I made a mistake, but I'm not glad. But anyway, I'll make the best of it. It is an easy mistake to make when you find out the diameter of something, to rush and stick it into the radius position in the formula and get an answer that is incorrect because of it. But I'm just going to have to move on. That is enough spheres. Yeah, I used the whole 10 minutes on these spheres. Let's do some more surface area of three-dimensional shapes and try to do something different. Let me look at my notes. Okay, I'm finished with that page of the notes because that was all about the spheres. Aha, okay, so quickly what I want to do is I want to find the surface area of both of these shapes that I actually folded together. I'll get rid of this list as well. Okay, there's my chalk. Now the cube, I'll do the cube first. The cube is rather straightforward. So the cube, I'll remind you, the side length was 2.5 inches because that was about the largest side length I could fit onto this piece of paper. So let's do the surface area. The surface area of a cube, now we could present this as a formula, but the surface area is going to be the total area of all 6 of these faces, like it was with the rectangular prism we did before. So the area of a square is equal to side length squared, and the side length was 2.5 inches. 2.5 squared is going to be 6.25. So I have 6.25 square inches, but that is the area of just one face, one of these squares. There are 6 of them. There they are. So I have to multiply by 6. It's going to be 37.5 square inches. And then we could talk about how, is it easier to deal with the actual three-dimensional object when we're answering a question like, what is the surface area of this thing? Or is it easier to deal with the net drawing? I'm trying to hold the drawing so that I can actually see the lines on the piece of paper, which can be a little tricky with the camera. Which is easier? I think it's a matter of opinion. I think I like doing it both ways, but I just really appreciate net drawings when I'm doing an exercise like that because of the way I can see all of the faces at once. Let's do the triangle pyramid. That's this one. Okay, I think it was 3 inches. Let me double check. Did I write it down anywhere? I'm going to have to measure it just to be sure, because I have a feeling I'm remembering that I used a larger side length for this equilateral triangle because I realized I could fit it. I could fit something larger. And yes, it is 3 inches. Okay, but then of course, when we do the area, it introduces a new twist. It is still one of the simpler 3D shapes because all 4 of the faces of that triangle pyramid happen to be the same because of the way I use an equilateral triangle as the base. So the area of a triangle is base times height over 2. Now that triangle though, I'll sort of draw a pretend version of it. It has a base of 3 inches, but the height is not going to be 3 inches. So we're in a position where I could measure it, but I don't want to measure it. The students that I am making this video for know how to use Pythagoras' theorem. So I have a situation where I can use Pythagoras' theorem. I'm going to use half of that triangle, which means that this base down, now I have a right triangle, so that's why that will work. Now this base is not 3 inches, it's 1.5 inches. And then, but this side here, the hypotenuse, is still 3 inches. Okay, I need more chalk. Here's another one of my chalk holders. Okay, so that is 3-inch hypotenuse. Okay, I'm moving off to the side and I'm doing my Pythagoras is like that. You're doing something else and suddenly you realize, ooh, I need Pythagoras, and you go off to the side and you do a Pythagoras. So c squared equals a squared plus b squared. C squared is going to be the hypotenuse, that's the 3 inches squared. I can call one of these A and the other B. I'll say the unknown I need, which is the height I need for my formula, is going to be the B. That means 1.5 is the A. Okay, 3 squared is 9, 1.5 squared is 2.25. 9 minus 2.25 equals b squared. Therefore, 6.75 equals b squared. B is therefore equal to the square root of 6.75. And what is that going to be? It's going to be 8 point something. Let's kind of guessing there. Square root of 6.75. 2.598. I'm going to call that 2.6. Does that make sense? Yes, it does. 2.6 equals b. Now we have what we need to do this formula. It's going to be a base. Now I'm not just doing the area of this little thing. I want the area of the whole face of my triangle pyramid. So therefore, I'm using this, and the base is 3. Times the height, which is going to be the 2.6, over 2, which is going to be 3 times 2.6 equals 7.8 over 2, which is 3.9. That is inches squared. But this time there are 4 equilateral triangles. There are 4 faces on that triangle pyramid that are all equal in area. So times 4 equals 15.6 square inches. Ta-da! That quickly, and it did take less than 10 minutes, we were able to find the area, the surface area of the cube and the triangle pyramid. Cool. And there's so many other shapes. I mean, I'm running out of time already, and I haven't even scratched the surface of all the shapes that I could be using. Fortunately, it's fun. Okay, what I want to do next is I want to challenge myself to do a couple of net drawings that are slightly more challenging than the cube and the equilateral triangle pyramid. So the ones that I chose, and we'll see if I have time to do both. I chose 2, but they're both square-based pyramids. Square-based pyramids. So let's see what I can put together here. Do I have enough chalk in this thing? Yes, I have enough chalk for the whole rest of the lesson. A square base. Now, convenient size for the chalkboard wall, I am going to make the base 12 inch by 12 inch square. So I'm using inches again. And I want to make sure I have room. So I'm picturing where I'm going to put the other faces of this pyramid. So I think I should have room if I put the square about here. So I'm drawing a 12-inch side, and then at right angle, another 12-inch side, and again I'm doing it freehand. Third 12-inch side. Where's my 12? There it is. And if these two are 12 inches apart, it means I did a good job of the freehand. And yeah, I did a pretty good job. Okay, so we have a square. That's a start, and it is 12 inches. So you can see, I'm not going to put the little right angle symbols. We can see it's 12 by 12, so yeah, it's a square. Okay, so we have that. Now, what am I going to do for the other 4 faces? There have to be 4 faces. I'm drawing a net. So, if I want the 4 triangles that are going to form the rest of my square-based pyramid to be equilateral, that means that I want 12 inch by 12 inch. There's more than one way of doing that. So what I'm going to do is I'm going to mark the midpoints, which I should have done just at the beginning when I was drawing this. I'm going to mark the midpoints, that's 6 inches, on all 4 sides of my square. And then, there's more than one way of doing it. I can break out my compass if I want, but I'm not going to. What I'm going to do is I'm setting 12 inches on this corner. I'm going to just draw a straight line and make it longer than I need. I'm drawing it faint. And I'm making sure this line is perpendicular to the side of the square. Drawing won't be perfect, but I just want it to be pretty good. Okay, so now what I'm doing is I'm getting the 0 of the ruler here and 12 inches on this vertex. And I am going to swivel the ruler until I can draw a line that is exactly 12 inches. And that came pretty close. So I estimated the sides of this little perpendicular line quite well. Same thing over here. Okay, I'm drawing a triangle pyramid. I'm drawing a net of a triangle pyramid. Well, this one I drew the line longer than I needed. Pretty good. 12 inches, 12 inches, 12 inches. So this is fun. It's taking a while though, so I have a feeling I won't be able to draw 2 of these after all. I'll just draw one. 12 inches. This one not drawn as well. That vertex is a little bit wonky. 12 inches. And finally, this one, and we have drawn a net, a little bit crooked that line, we have drawn a net of a square-based pyramid, and now what's left is to find the surface area of it. The middle part is easy, right? The area of a square is going to be equal to side length squared, which is 12 squared, which we all know is 144 square inches because we know our multiplication tables at least up to 12 times 12. And then there's the 4 triangles. Well, I'm going to have to do this 4 times, but they're going to be equal to each other. And the triangles, the area is base times height over 2. The base is it's 12 inches. But what's the height? Again, I can find the height with Pythagoras, or I can measure it. This time, because I am running low on time, I am going to measure it. So this is not going to be a perfect measurement. It's going to be close. Oh, it's right around 10. What did I get when I did? Yes. I did actually calculate it before. So, Pythagoras, this would be 6. Yeah, I have it on this page somewhere. Where's my 6? Oh, that's what I did. I got all the way to the point where I needed my calculator, but I didn't have my calculator. So I need the square root of 108. 10.4. That's what it is. It's going to be 10.4. That's the measure of this little height that I drew up here. 12 times 10.4 over 2 is equal to, 12 divided by 2 is 6. So I'm just doing 6 times 10.4, 62.4. And then, because I've learned my lesson, I will get my calculator and I'll double check that. 12 times 10.4 equals divided by 2 equals 62.4. That's good. Inches squared. But there are 4 of these triangles. Times 4 equals 249.6. Yes, 249.6 square inches. But I need to add the area of the square at the bottom, plus 144, plus 144, 393.6 square inches. So we were able to piece together the areas of the two-dimensional shapes which come together in our net to form the three-dimensional object, which this time is a square-based pyramid that happens to have equilateral triangles as the other 4 faces. And we have calculated the area. So a lot of the calculation of surface area will be kind of pieced together like this, because it's not always going to be really convenient the way it is with the cube, where you find the area of one square and then you just have to multiply it by 6. How am I doing for time? Don't really have time to do another drawing. So what I'm going to do is I'm going to I don't really want to do that either. A list of shapes. Yeah, that's what I'm going to do. I'm going to say, wait, what if, because I'd like to get into this. It might seem to some students, especially for beginners in this topic, that, well, do the sides, do the faces, these 4 triangular faces, do they have to be equilateral? And I think you might realize from the way I've been talking about it that no, they don't. They do have to be equal to each other if you want it to work as a pyramid. And the best way to experiment with that is, yes, draw the net. Now I did draw the nets, I just didn't draw them big enough to cut out. So you see there's one. This is my drawing of the one that's up here. And then I drew another one over here. There's a drawing where the triangles are actually, they're isosceles. And I think that kind of has to happen. They're isosceles, but they're not equilateral. So in my other drawing, which I'm not going to draw because I don't have time, instead of this being 10.4 inches long, this height, I made it 18 inches long. So what I'll do is I'll modify just this one over here, 18 inches. And we'll sort of redraw part of this net to see what it's going to look like. 18 is way over here. Okay, so what I would do, I guess I can try the colored chalk, as colored chalk doesn't really work very well on video. But if I connect this to here, see, the chalk is orange. Can you tell it's orange? And connect this there. Aha! So I have another net where the 4 triangles are all as big as that orange one. And it still works. It will still work to successfully fold together and make a square-based pyramid, but it'll be taller. So what would the surface area of that one be? Some of the work's already done for us. That's good because we don't have much time. The area of the square is going to be the same. But the area of the triangle, well, the height isn't 10.4 anymore, it's 18. So I'll just do that right over here. Area equals base times height, which is 12 times 18 over 2, which is easier to do in our heads. 12 divided by 18 divided by 2 is 9. 9 times 12, that's 108. 108 square inches instead of 62.4, but I still have to multiply by 4. So that is going to be 432 square inches. And then when we add the 12 inch by 12 inch square plus 144 equals 576 square inches. That was interesting. That went faster than I expected, but it's because we preserved that same size square when we decided to add this extra example. There are so many more really interesting shapes. Just square-based pyramids. I could do so many different things by playing around with the side length of the square or playing around with the height of the triangles. and you end up with different answers, but you also end up with different and really interesting challenges if you try to draw the net. And then even draw the little tabs and cut it out with scissors and fold along the lines and see if you made it work. Because it is possible that a student would draw a net that looks like a correct answer, but then when they actually fold it together, they realize, uh-oh, made a mistake. But that's good, because when that's happening, learning is happening. There is so much to learn in three-dimensional geometry that playing around with a lot of this stuff is really going to help. And with that, I am going to say thank you for being here. It was fun as usual. The hour flew by as usual. The dog is starting to realize that it is finally supper time, so I'm going to just pick her up so she can wave goodbye, and then I am going to end the class. Okay, you up, 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 up. There you are. It's so nice to see your eyes. I bet you by next week when I make the next video in this series, we won't be able to see your eyes. Okay, thank you very much for being here, and I will see you next time.